All right. So up till now, we have started our discussion of inhomogeneous second order linear differential equations. So we have been looking at equations of this form. Y prime plus q of xy equals some r of x, right? So a physical or engineering interpretation of this equation would be that r of x is some kind of a driving that is driving the system, right? So some external input that is driving the system. So r of x is usually in your hands. You can tune it up or down or things like that. So we can see certain examples of these things as we go along or in the tutorial problems also. We also discussed that the general solution of these equations can be written as a solution of the homogeneous part plus a particular solution. And then we discussed certain properties of these solutions, existence and uniqueness and all those things. But all those is predicated on the on you being able to find this YP, this particular solution. So I hope that by now, at least for constant coefficient problems, the YH part is fairly obvious to you. So we considered equations of this form, ay prime plus by equals 0. This is the constant coefficient problem, and we discussed various cases. And I will not belabor this point. So hopefully by now, this should be obvious to you. Now we will add up the difficulty level slightly by still sticking with these constant coefficient problems, but making the right-hand side non-zero. So ultimately, we want to get to equations of this sort, where the coefficients are also functions of x, right? Some arbitrary functions of x. But we will get to that by first considering equations of the form y double prime plus ay prime plus by is some function of x, r of x. And we want to be able to solve equations of this kind. And there is, as long as the function r of x is simple, like for example, simple polynomials and simple sines and cosines and exponentials, there is a certain rule book that is also given in your textbook that is fairly easy to follow. Of course, I could just give you what this rule book is, and you could simply apply it and be happy. But I want to slightly motivate where this comes from. Okay, so in this lecture, I will certainly use the rule book, and I will tell you what the rule book is to solve this equation for easy enough functions on the right-hand side. But I'll also tell you a little more about how to get this rule book and why this rule book makes sense. Okay, so I will do this with a series of examples. So my goal in this class is to try and figure out ways of figuring out the particular solution. So the homogeneous solution for this equation should be very clear to you. As long as I tell you what A and B is, you can find the roots of the characteristic equation. And then the general solution is A to the alpha 1x plus B to the alpha 2x, where alpha 1 and alpha 2 are the roots of the characteristic equation. Okay. In fact, you could simply write down the general solution as the homogeneous solution, which you can easily figure out, plus YP. So let us try and figure out YP. So example 1. This is a very simple case. So what's the easiest way to find YP? So let us take the easiest example. So y double prime minus 2y prime, I don't know, plus 3y, 4y, whatever it is, equals 5. The right-hand side is a constant. It's not even a function of r of x. Okay. Now notice that this is still an inhomogeneous equation, right? I cannot factor this as something acting on y equals 0 because there is a y independent part on the right-hand side. So this is still an inhomogeneous equation, more complicated than this guy, but still fairly easy to understand in terms of figuring out the particular solution. Of course, I can figure out what the homogeneous equation is and its solutions are, but the easiest way to figure out the particular solutions in this equations of this form is simply by staring at it, simply by inspection. Okay, so if you look at it a little closely, you will be disappointed to see that the particular solution for this guy is just a constant. You might disagree that this is too trivial, but as I've repeatedly emphasized, as long as a solution obeys the property that if I plug it back into the equation, it obeys the equation, then I'm golden. Okay, so this is a very simple case where if you only have a constant on the right-hand side, the particular solution also can be written as a constant, as long as the left-hand side is linear in all these variables. Okay. Of course, I could still have a y square and this will still hold, but I should just figure out a different constant. But anyway, we'll be looking at equations of this form, and this certainly works, right? Y prime and y double prime in this case are 0 for the particular solution. And if I plug y is 5/3, the last term gives me 5, which satisfies the equation. So let's move on to a slightly less trivial example.
So is there a reason why yp is equal to 5/3? Like, or is it just a rule?
No, it's not just a rule. So my point is that in cases like this, you can simply guess the particular solution by looking at the equation. See, the way I'm motivating the subject at least is that you should have some kind of a toolbox to figure out these equations whenever you see them in your engineering studies, right? So that is the point. So if you look at an equation like this, you can easily guess that the particular solution is just a constant, because if I plug this in, so plug in yp equals 5/3 in the equation, you would actually find that this satisfies the equation, right? Yp double prime is 0, minus 2 yp prime is 0, plus 3 times yp is basically 5. So this certainly solves the equation. You can take this as a rule. For example, if you have any equation of this form, ay prime plus by equals some n, where n is a number on the right hand side, then y equals n over b is a particular solution. Okay. Of course, this is a very simple example in which the particular solution is rather obvious to you, but it is still worthwhile to look at. Is that okay?
Yes, sir.
So if you want to elevate it to a rule, by all means do so. Okay. A slightly less trivial example is y double prime minus 6y prime plus 9y equals 8e to the x. Of course, in this case, the right-hand side is not a constant. In this case, can I figure out the particular solution? Well, even in this case, inspection works, but you have to work a little bit harder. For example, if my y is e to the x itself, if my yp is e to the x itself, okay, then what happens? Well, there is a hope that this will solve the equation. The reason is, if I plug in e to the x, right? So if I try yp as e to the x, then of course yp prime is also e to the x and yp double prime is also e to the x, right? So then if I plug this in the equation, you would get e to the x minus 6e to the x plus 9e to the x, which is not quite 8e to the x, right? So yp equals e to the x doesn't solve this equation. But of course, the trick here is to recognize that the function on the right-hand side is such that the derivative of the function is the function itself, or some simple form of the function. Okay, so I have e to the x. So y prime also is e to the x and y double prime is also e to the x. So ultimately, whatever the left-hand side is, I'm going to get something times e to the x. Okay, so in this case also you can guess. So y equals e to the x certainly doesn't work, but you can easily satisfy yourself that if I try yp equals 2e to the x, this will indeed work. Okay. So yp equals 2e to the x is indeed a particular solution of this equation. So you can easily check. So yp prime is 2e to the x. Yp double prime is 2e to the x. So plug everything. Yp double prime minus 6yp prime plus 9yp would be equal to 2e to the x minus 6 times 2e to the x plus 9 times 2e to the x, which is 2 minus 12 plus 9 times 2. So 18 minus 12 is 6, 6 plus 2 is 8. So this is 8e to the x, and this does solve the equation. Of course, you still have to check one more thing, which I will not do now. The question is this particular solution different than the solution to the homogeneous part? See, when I write the solution as yh plus yp, there is an intrinsic assumption here that yp is not just yh, right? So if yh turns out to be, let us say, e to the x plus e to the minus x, you should not write yp is also e to the minus x, because it is already contained in the solution for yh. So yp should be distinct from yh. So in this case, you will actually find that it is indeed distinct, and this does indeed solve this equation. Admittedly, this is a slightly less trivial example, but it is still easy by inspection because the function on the right-hand side has a very simple property, that whose derivatives are very simple. The question is, suppose if I have any function like e to the x on the right-hand side, can I always solve it in this fashion? Well, let us try. Y double prime plus y prime minus 2y equals e to the x. Suppose if I write yp equals e to the x, would this solve this equation, or any multiple of e to the x, would this solve the equation? The answer is it won't. There is a reason why it won't, because try yp equals e to the x, and you would actually find that you can even try n times e to the x. It doesn't matter. The n just factors out of the equation. You would actually find that yp double prime plus yp prime minus 2yp is actually 0 in this case. Okay. So here's an example where the same logic as example 2 fails. Even though structurally this equation looks rather similar to the example 2, where I only have an e to the x on the right-hand side, a simple yp equals e to the x or some multiple of e to the x doesn't work in this case, because if I plug it back into the equation, it actually gives me 0. Another way to interpret the same equation is that this particular solution doesn't work because e to the x in this case is actually a solution of the corresponding homogeneous part. So e to the x is already contained in the homogeneous part, so you cannot have that as a particular solution. Okay. So the question is, how would you solve equations of this form to get the particular solution? I will first tell you the laborious method, and then I will motivate the rule book. So let us actually solve this. And there is a way to solve this equation. But before I solve this equation, I'll give you another example. Okay, I'll bore you with lots of examples. So now I will use the shorthand notation d equals ddx, even though I'm not supposed to. So don't tell anybody. So let us look at the equation. Let us say d minus 1, d plus 5 equals 7 e to the 2x. Okay. So we will solve example 3, and then I will also give you the solution for example 4, and then we will contrast. Okay, and then we will see what the difference between these two cases is. Okay, so let us go back to example 3. Example 3 is y double prime plus y prime minus 2y equals e to the x. Okay, and I want to solve this equation. So I can write this left-hand side as, let us say, d minus 1 times d plus 2 y equals e to the x. Any questions or comments about this? Does everyone agree? In case someone is uncomfortable with me using this notation, please let me know. I will switch back. All I mean is that, I can find out the roots of the homogeneous part very easily. The roots will turn out to be 1 and minus 2. So I'm basically writing this equation as ddx minus 1 times ddx plus 2. That's what roots actually mean. Okay. Is this okay? All right. So now I will actually solve it by direct integration. So I will assume that this function d plus 2 times y is some function u of x. Okay. So after all, this is just d dx plus 2 acting on y, and this is obviously some function of x. So I'll call this function u of x. And I'll plug this back in the differential equation. What is this differential equation now? This is d dx minus 1 acting on u of x equals e of x. So again, notice that this is now a first order differential equation for you, which you theoretically know how to solve because you know how to write down the general solution for a first order differential equation. Okay. So what is the solution? I will write this equation as u prime minus u equals e to the x, or this is of the form y prime plus p of x y equals r of x, right? And we wrote down the general solution in this case. Y of x is, what is this? E to the minus h times integral e to the h r of x dx plus some constant. where h was integral p of x dx. Okay. Is this familiar or is this too fast? Is it okay? Everybody? So p of x in this case is just -1. So h in this case is integral minus dx, which is just minus x. Okay, so let me write down the solution for this equation, which I will call equation number 1. Solution for this is u of x equals e to the minus h, which is e to the x, times integral e to the h, which is e to the minus x, r of x. R of x is a stuff on the right hand side, which in this case is just e to the x. So e to the x dx plus some constant, which I will call c1. And all said and done, you can easily do this integration and you will get your answer as x e to the x plus c1 e to the x. Okay. So you have figured out u of x by a direct integration. Now I will plug it back in the differential equation. My differential equation is, of course, d plus 2 times. So remember, d plus 2 times y is u. That is what I have found out. D plus 2 times y is u of x, right? So d plus 2 times y is x e to the x plus c1 e to the x. Now I have a second first order differential equation for y. So basically, in this simple case, I have broken up a second order differential equation solution as two successive first order differential equations, which I know how to solve. Again, I will write this in the familiar form, y prime plus 2y equals x e to the x plus c1 e to the x. Okay, so in this case, h is integral p of x dx. P of x is 2. So this is 2x. And r of x is, of course, x e to the x plus c1 e to the x. And I will not bore you by figuring out the entire solution. You can simply write down what the solution is using the exact same formula. And you will actually find that y of x equals 1/3 x e to the x plus some constant c1 prime e to the x plus some constant c2 e to the minus 2x. Okay. You can directly integrate this again to find the solution y of x, and the solution y of x will turn out to be of this form. In this case, we have not used any trick. We have not used any rules. We have not used any shortcuts. We have honestly sat down and solved this equation by two successive integrations. Yes.
Sir?
Yes.
Sir, you have assumed d plus 2 times y is equals to u of x.
Correct.
So, but sir, y is also a parameter in that. No?
Correct. So I don't know what y is, right? So I'm trading one function for another. So I'm basically saying that, look, this is the equation that I have to solve, right? Now I can piece this different. Now, if you want, you can also write this exact same equation as d plus 2 times d minus y equals e to the x, right? Both give you the exact same differential equation, y double prime plus y prime minus 2y. Now, if you want, you can treat this as some function of x. See, y is a function.
But y was as a function of x. We have y, right?
Yes, but it is some function of x, right? So I don't know what y is, right? See, if I don't know what y of x is, I don't know what 5 times y of x is. I also don't know what y prime of x is. I can as well call y prime as some other function g of x. Nobody can stop me, right?
But we are assuming that the whole expression will be something as a function of x only, purely.
Correct, because my goal is to find y as a function of x. That's what I mean by
okay, yeah.
Yeah. So there is no cheating involved, I assure you. Any other questions or concerns? So does everyone believe that we have done an honest job in this case? So basically, I appealed to the roots of the homogeneous equation and wrote the left-hand side in this particular fashion. And then this is basically similar to what we did for finding the second solution if one solution is given, right? So there we employed an analogous trick, not the exact same trick. But basically, I'm trading one variable for the other and converting a second order equation into a first order equation. I can always do this. Now notice that you can at this point tell me that you could have figured out this part yourself. Why? Because this part, after all, is the solution of the homogeneous equation. What is the homogeneous equation in this case? In this case, the homogeneous equation is, of course, y double prime minus 2y prime. What was it? Sorry, plus y prime minus 2y, right? Plus y prime minus 2y equals 0. And the solutions, let me write this as yh, right? And the solution of this is, of course, c times e to the x plus c2 times e to the minus 2x, where 1 and minus 2 are the roots of this equation. This you already know. So this you could have figured out. But by directly solving the equation, we also get this term. And this term I will interpret as the particular solution of this particular, of this problem. Excuse me. So this is my YP for this problem, and this is something you already knew. Of course, since we are doing it from scratch, we got everything. Okay. So I invite you to do example 4 now. Now notice that x e to the x has nothing to do with e to the x or e to the minus 2x. So this is also answering a question that somebody raised in last lecture. So you told me in the homogeneous case that y1 and y2 are independent solutions. So what about yp? Can it be trivially gotten from yh? The answer is not always. Okay, yp is not trivially obtainable from yh. If it were, then we would not need all these procedures. Okay, so let us go back to the other example that I wrote down for you. And I strongly encourage all of you to do this example yourself out. I'll give you the solution, d minus 1 times d plus 5. D minus 1 times d plus 5y is 7 e to the 2x. If you don't want 7, you can just make it 1. It doesn't matter. The 7 is not important. The 2x is important. Okay. The solution for the homogeneous part again is very obvious to you. It is e to the x and e to the minus 5x, right? So the question is, what is the particular solution? Again, do the exact same procedure that we just did, and you will find that the general solution in this case is actually C1, excuse me, e to the 2x plus C1 e to the x plus C2 e to the minus 5x. Okay. So this again, as before, is just the solution to the homogeneous part, and this is the particular solution. Okay. Now again, please derive this in exactly the same way we derived the previous solution. And with these two examples, I hope to impress upon you that figuring out certain simple rules is often more useful than doing these laborious calculations every time. So notice that the equation that we were solving in the first case is y double prime plus y prime minus 2y is e to the x. And the particular solution turns out to be x times e to the x. Okay. The second case, the particular solution is actually quite simple. Here, the roots of the characteristic equation are 1 and minus 5, and the e to the exponent of e to the x is 2, right? And if that were the case, the particular solution is exactly the function on the right itself. So you see that in this case, there was e to the x on the right-hand side, but the particular solution was x times e to the x. But in this case, there was e to the 2x on the right-hand side, and the particular solution is e to the 2x. It turns out that it is not dependent on whether it's e to the x or e to the 2x, but whether or not this number, right, 2 or 1 or whatever it is, matches with one of the roots of the left-hand side. So in the first example, the roots of the equation was 1 and minus 2. You see, so if the one of the roots was 1 and the right-hand side is also e to the 1 times x, then e to the 1 times x cannot be a particular solution because it is already contained in the homogeneous part. You see, so that is the difference between these two examples. In the second example, the roots of the homogeneous part are 1 and -5, and the exponent on the right hand side is 2 times x, which is 2 is neither 1 nor -5. So if that is the case, then the particular solution is simply just the function itself. Now, you could also have a case where you have a solution like, let us say, so this is not strictly an aside. This is also part of your vocabulary in this case. You could also have a situation like d minus 1 the whole square y is e to the x. Okay. So in this case, now x times e to the x would also, in this case, obviously 1 is a solution, right? In fact, 1 is a double root. So the YH on the right hand side would now be C1 plus C2x times e to the x. So now notice that unlike in the last two cases, the particular solution cannot be e to the x because it is already in the homogeneous part. It cannot be x times e to the x also because it is also in the homogeneous part. So I invite you to do this again on your own, assuming that d minus 1 times y is u, and you will find that the solution to this guy, the particular solution, would turn out to be something like x squared e to the x. Okay. So doing these three examples in long form actually will convince you that there is three classes of problems if you have a simple function like e to the x on the right hand side. So I will motivate this so-called rules. And if I motivate them for the exponential case, they're the exact same rules for the other cases also. Suppose if I could write my differential equation, whatever my differential equation is, right, y double prime plus p of x y prime plus q of x y equal to r of x, where r of x is some. In this case, I'm looking at some, let us say, e to the alpha times x. Okay. Now, there is three classes of particular solutions in this case. So I can write this homogeneous part of this equation as some d minus lambda 1 times d minus lambda 2y. Okay, and this equals e to the alpha x. Then the three examples that we have written down, example 3, example 4, and this guy, which I have not labeled. So you can call this example 5 if you want. Motivate us to claim that there is three classes of particular solution that you can write for problems of this kind. Yp would be equal to c times alpha x itself if alpha is not equal to any one of the roots. Okay, and obviously lambda 1 and lambda 2 are distinct. That is inbuilt. Okay, it will be equal to c times x times e to the x if alpha is equal to lambda 1 or alpha equals lambda 2. Okay, and lambda 1 and lambda 2 are not the same. And it will be c x squared e to the alpha x if all of them are the same. Okay, so the third case is for a double root. If you have a double root, the particular solution will be x squared times the e to the alpha x on the right. If you have the alpha matching with one of the roots on the left hand side, then your particular solution that you have to figure out is x times e to the alpha x, which is what we did in this case. Right? We actually figured this out because in this case the root was 1 and it was matching with the right hand side was e to the x, 1 times x, and 1 was matching with one of the roots, right? So you could actually either do it out every time explicitly, or you could simply remember these rules. Obviously, remembering this is not very difficult, and I encourage you to do so. But I still want you to figure this out yourself, like do out the example 4 and even example 5 laboriously and convince yourself that it'll be rather silly to do this out every time. Do you have any questions about this?
So in the first thing where we've written that yp is equal to c per alpha x, so like one of the conditions is that lambda 1 should not be equal to lambda 2. But what if we have a case where alpha is not equal to lambda 1 and lambda 2, but then lambda 1 and lambda 2 are equal? Like we have a double root, but then alpha is not equal to that root.
Oh, so then this case applies. So lambda 1 not equal to lambda 2 is obviously not very important. So maybe I'll just take this off. Thank you. Okay, so the alpha matching the root is what is important. So if alpha doesn't match any of the two roots, then your particular solution is just e to the alpha x. If alpha matches one of the two roots, then your solution is x e to the alpha x. Of course, if you have a double root, then and if your alpha also matches, then it is x squared e to the alpha x. Make sense? So you do this out yourself. So let us again, the best way to convince yourself is to actually do this. So let us say you have an equation like this: d plus a whole square y is e to the bx, where b is not equal to a. Okay, if you want, you can put some values, a equal to 1 and b equal to 2, and do this in the laborious way as I just did, and figure out what the particular solution is, right? It will be a good exercise. Okay. Maybe I'll put one of these as a tutorial problem so that you have some practice and you actually convince yourself that the procedure is actually true and it works. Okay, so now it'll be rather silly if it only works for exponential, because there is no point giving you rules if it's only going to work for one particular case. But obviously, you can easily guess that if it works for exponentials, it's also going to work for sines and cosines. But before we do that, let us actually figure it out. Let us apply this rule and figure out. So basically, I have a C here, you see, and I should fix what the C is, because I told you at the very beginning that the particular solution is not supposed to have any undetermined constants. Now, so remember again that the general solution is YH plus YP. And YH can be written as C1 Y1 plus C2 Y2, where Y1 and Y2 are the two linearly independent solutions of the homogeneous equation plus YP. Now here, cavalierly, I've written YP as some constant times e to the alpha x or some constant times x e to the alpha x, but I better determine what the constant is. And to determine the C1, C2 in the general solution, I'll have to appeal to the initial value conditions. But to figure out what this C is, right, I cannot appeal to the initial value problems. That is only applicable to find C1 and C2. This capital C you will figure out by simply demanding that this particular form solves the equation. So I'll convince this is true by doing the example that we solved laboriously. So this example, where in this case, my particular solution was 1/3 x e to the x, right? So again, in this case, I'll go back to example 3 and I will use the rule book this time. So example 3 can be written as, what was this? D minus 1, d plus 2 is e to the x, right? D minus 1, d plus 2 y is e to the x. Or if I want to write it in y double prime plus y prime minus 2y equals e to the x. And I know that this is a case where alpha is matching with one of the two roots. So my particular solution should be cx e to the x. Alpha is just 1 in this case. So this much I know. But I'll need to figure out what c is. To figure out what c is, I'll plug this back into the equation and demand that it solves the equation. So with this ansatz, what is this differential equation? Yp prime would be c times e to the x plus x e to the x. Yp double prime would be c times, differentiate this, it will be e to the x, again e to the x plus x e to the x plus 2e to the x. Okay, make sense? So plug everything back in the differential equation. What do we get? So Yp double prime would be c times, there will be a c that can be factored out, and y double prime would be x e to the x plus 2e to the x, plus y prime would be e to the x plus x e to the x, minus 2y would be minus 2x e to the x. And this has to be equal to e to the x. So my c should be such that this equation is true. So there is 2 factors of x e to the x and 1 factor of minus 2x. So this and this would cancel, which would tell me 3c e to the, oh, sorry, wrong color again, which would tell me that 3c e to the x is e to the x, or c is 1/3. Okay, so I'll figure out c by appealing to the differential equation itself. Okay, so this is exactly what we found here also. Sorry, here, 1/3 x e to the x. Okay, so again, to figure out the constant in the particular solution, demand that your form for particular solution is indeed a solution that will fix the constant. You should not appeal to the initial value conditions. Okay, so now let me quickly tell you that this is actually true for sines and cosines also. I'll simply motivate this. So suppose if I have sinusoidal function. Okay, a famous example of a sinusoidal function is what is called a driven harmonic oscillator. A driven oscillator. Okay, in this case, I will have my double prime plus c y prime plus ky. This is an equation you already studied. C is the damping and K is the Hooke's law guy. And depending on whether it is overdamped or underdamped or whatever it is, you know what the motion is going to look like. If it is overdamped, it's going to exponentially decay. If it's underdamped, it's going to oscillate, but it's the amplitude of oscillation is going to keep getting smaller and finally exponentially decays. And if it is undamped, of course, it just keeps oscillating. But assuming an overdamped or underdamped, now I can keep the oscillator in motion by driving it with an external force. Suppose I write f cosine omega t, a sinusoidal function. I can drive it with any force I want, but if I choose a sinusoidal function, then what is the motion like? Okay, so this is a very interesting example, and unfortunately, I will not have time to cover this in class, but I will write a tutorial problem for this, and I really want you guys to work out, and we will discuss this in the tutorial. So the question is, how do you deal with problems of this kind? Okay, so let me take an example again. What is this example number? Example. We are done with 4, right? So let us do 5. Y double prime plus y prime minus 2y is 4 sine 2x. Okay, I'll be very brief here. Now I will look at this equation and I will tell you that, well, look, let me solve an equation that I know how to solve. Okay, so this is something that physicists always do, probably mathematicians also do. If you're looking at a complicated equation or an equation that you don't know how to solve, you convert it to something that you do know how to solve and see if you can gain some insights from that. So let me solve it slightly different equation, y double prime plus y prime minus 2y, I'm writing capital Y, equals 4 e to the 2ix. Why am I looking at this equation? Well, I can, so since the right hand side is complex, the solution can also have a complex part. So I can assume that y has a real part and a complex part, right? So if I plug this and equate the real and imaginary components, I will get 2 equations from this guy. I'll get y real plus y real prime minus 2y real is 4 cosine 2x, and y imaginary plus y imaginary prime minus 2y imaginary is 4 sine 2x, which is obvious. We can simply plug this on sorts and write e to the 2ix as cosine 2x plus I sine 2x and equate the real and imaginary parts. And you find that the imaginary part of this is exactly the original equation. Okay, if I put capital Y as little y, that is what I have. So basically what I believe is that instead of solving this equation that I don't know how to solve, I will solve this equation, which I've just figured out how to solve. And then I will simply take the imaginary part of the solution, and that should give me the solution for the original equation that I'm looking for. Okay, is the assumption clear? So since I don't know how to solve for sinusoidal functions, I'll solve for exponential functions. And then I can decompose this into a real and imaginary part, and the imaginary part exactly matches with what I have. Okay, if I had a cosine 2x, then the real part will match with exactly what I have. So I will take the real part of the solution to be the particular solution of the original problem. So depending on what your problem is. Okay, now this I know how to solve. So y double prime plus y prime minus 2y is e to the 2ix, sorry, 4e to the 2ix. Okay, the homogeneous part, of course, has a solution. Homogeneous part has a solutions. You can easily check that this is yh equals, the roots of this would be c1 e to the minus 2x plus c2 e to the x. Okay. Now what I have on the right hand side, see, first of all, these roots are real, they are not complex. So obviously neither minus 2 nor plus 1 is equal to the exponent on the right hand side, which is 2y. So 2y is not equal to either minus 2 or 1. So in this case, my particular solution can be simply written as yp is some c e to the 2ix. Okay. This is the first rule. The first rule is this guy doesn't match either one of these roots. In this case, it doesn't, because the roots in this case turn out to be real, luckily, and what I have on the right hand side is complex. What is C? Again, substitute and find out. I will leave that to you, and you can actually show that in this case, C can be, so substitute this back in this original equation. Okay, so I'll just show it to you once. Yp prime would be C times 2i times e to the 2ix. And yp double prime would be c times 2i whole square, which is minus 4 times e to the 2ix. There's no reason to write the x as a capital. Sorry about that. Okay. And substitute everything back, and then you will get c times y double prime is 2i e to the 2ix minus 4 e to the 2ix minus 2 e to the 2ix equals 4 e to the 2ix. Okay, and this will give you some complex coefficient, and you can figure out that this is equal to actually minus 5 times I plus 3. Okay, so now what is my particular solution for the modified problem that I made up? The particular solution for the modified problem I made up is minus 1/5 I plus 3 e to the 2ix. What is the particular solution for the problem that I was told to solve, which is this? Well, the particular solution for this guy is just the imaginary part of the particular solution for the problem I made up. So yp is just the imaginary part of yp. Okay, which means this guy is equal to, you can actually figure this out. Take the imaginary part of this guy, you will find that this is equal to minus 1/5 cosine 2x, if my calculations are right, and I certainly ask you to check, minus 3/5 sine 2x. Okay, so notice that since I have basically converted these sinusoidal functions into exponential functions, every rule that applies to the exponential functions should also apply to the sinusoidal functions. Okay, so same, it's the same deal. So if the roots are this thing, blah blah blah, then I should have this then I should have c to the 2ix, and if the root in this case matches one of them happens to be 2i, then I should have had yps cx e to the 2ix, and so on and so forth. Again, you can do everything in this laborious fashion, or you can figure out rules. The same rules like the exponential case also hold for the sinusoidal case. So now I will summarize these rules from your textbook, and then you can simply use these rules instead of doing everything out laboriously yourself. So this is r of x, and this is the corresponding yp. Okay, so if r of x turns out to be k e to the gamma x, your choice is c e to the gamma x, but with a caveat. The caveat is what I mentioned. I will write that down explicitly. If r of x turns out to be a polynomial, where n equals 0, 1, 2, blah, 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 or just a power of x, not a polynomial. We'll come to polynomials in a second. Then yp of x is in general a polynomial whose highest degree is the power that appears here, n. So if r of x is kx squared, then yp would be some constant plus some constant times x plus some constant times x squared. So, okay, this would be some c0 plus c1x plus c2x square plus all the way till cn x to the n. Okay. Not x to the n plus 1. So if the r of x is cubed, you stop with a third degree polynomial for the particular solution. Again, how do you figure out the constants? Plug it back in the differential equation, demand that this ansatz solves the differential equation, and fix the constants. If it is sinusoidal, then you simply try a cosine omega x plus b sine omega x. You can do it out in this laborious fashion that I just explained to you. I wanted to motivate that. But notice that the particular solution in this case is some linear combination of cosine 2x and sine 2x. So remember that the equation that we are solving for r of x in this case was sine 2x. And my particular solution turned out to be some linear combination of sine 2x and cosine 2x. Okay. So instead of doing it this way, you can use this rule that if you have a cosine omega or a sine omega x, your particular solution is a linear combination of cosine and sine. The last one is k e to the alpha x cosine omega x and k e to the alpha x sine omega x. For both these cases, your trial e to the alpha x should be a cosine omega x plus b sine omega x. Okay. The caveat is as follows. The caveat is if you have so in the first case, we explicitly showed you that if the gamma happens to be one of the roots, if the particular solution happens to be the same as the homogeneous solution, then multiply it by x. If the particular solution happens to be the same as both the homogeneous solutions, in case of a double root, multiply the particular solution by x squared. We demonstrated this for the exponential case, but this is also true for any of the other cases. Okay, so if yp happens to be a solution of the homogeneous equation, multiply the ansatz yp by x. Okay, if y matches a double root, then multiply by x squared. Okay. Now the third important rule which makes the entire thing so easy is if r of x is a sum of the terms in the table given above, then yp is a linear combination of the individual particular solutions. Okay, in other words, if my r of x is e to the gamma x plus cosine omega x, then the yp, so example, y double prime plus ay prime plus by is e to the alpha x plus cosine omega x. In this case, the yp that I will try is some c e to the alpha x plus a sine omega x plus b cosine omega x. I'll fix a, b, and c by feeding it back into the differential equation and equating the coefficients of the various terms. Okay, not by appealing to the initial value conditions. Okay, so I hope that with this knowledge you can go back and solve some of the tutorial problems that were given to you, which I could not solve. So I will just briefly sketch one of them that has all these ideas. One of the problems in your tutorial section last week was 8y double prime minus 6y prime plus y is 6 cos x The initial values are y of 0 is 0.2 and y prime of 0 is, I don't know, 0.05, whatever it is. So how will you solve this initial value problem? So notice that the differential equation can be written as 8y double prime minus 6y prime plus y is 6 e to the x plus e to the minus x over 2. That is after all what cosine hyperbolic is. So this is basically 3 e to the x plus 3 e to the minus x. So it's a linear combination of x and 1 and minus 1. So the first thing to check is what rule should you apply. So look at the roots of the characteristic equation or the homogeneous equation, and you will find that the two roots are lambda 1 is 1/2 and lambda 2 is 1/4. So you can write down the homogeneous part as some c e to the x over 2 plus c2 e to the x over 4. And you will fix C1 and C2 by looking at the initial values. Okay, so I'll tell you how to do that, not just looking at YH. Now, what is YP? YP would be, if I had only e to the x, I will try some k1 e to the x, but I have e to the x and e to the minus x, so I'll try k1 plus k2 e to the minus x. I'll take like 1 minute more and finish this off. Sorry about that. So now, I'll have to first fix K1 and K2. I'll fix K1 and K2 by demanding fix K1, K2, demanding that YP solves the given equation. So 8 YP double prime minus 6 YP prime plus YP equals 3 e to the x plus 3 e to the minus x. How will you solve this? So you will plug this onsorts back here, and you will equate all the coefficients of e to the x and all the coefficients of e to the minus x, and that will give you k1 and k2. So do this and you will find that yp is actually equal to the coefficient k1 should be 1 and the coefficient k2 should be 1/5. So now I can write the general solution as c1 e to the x over 2 plus c2 e to the x over 4 plus the particular solution, which is e to the x, plus 1/5 e to the minus x. Okay. And now I will impose the initial value conditions to figure out C1 and C2. So don't impose initial value conditions only on the homogeneous part. Because you're actually solving an inhomogeneous differential equation, you should impose the initial values on the complete solution. You're not solving homogeneous ODE, you are solving an inhomogeneous ODE. So you should impose the initial value conditions on the entire stuff, not just on this part. Okay, so this is a mistake that you can make in haste. So please guard yourself against that. So now demand that for this guy, y0 is whatever is given to you, 0.2. And y prime at this is 0.05. And this will fix C1, C2. Okay. So the important things to remember are, you fix the coefficients of the particular solution by demanding that the particular solution solves the differential equation. Your onsorts for the particular solution solves the differential equation. And you fix the coefficients of the homogeneous part by appealing to the initial value conditions. But you should look at the entire equation. You should impose initial value conditions on YH plus YP and not only on YH or only on YP. That will be a mistake. Okay, so the way you fix these coefficients are slightly different. And for this reason, this method is called method of undetermined coefficients. So whatever we have talked about today, it goes by the name of method of undetermined coefficients. Okay, so basically you're just fixing the coefficients by appealing to these rules for the case of very simple choices of R of X. Okay, so I'll stop here.